Okay, so thanks everyone for coming. I'm always happy to be back in Berkeley. Just realized I first was here 23 years ago when I started my PhD. So now you can see how old I am. But it's always nice to be back. And I'm gonna talk about quantum machine learning in the NISQ era. And it's not very clear to me what quantum machine learning is, neither what NISQ is. So I will try to basically open a discussion about all of these things. So the goal is that many of us are going to stay here for a few weeks or months. So just trying to, start some conversations and discussions. So, there will be some new results, some opinions, and some provocative statements in the talk. So let's see how it goes. Okay, so this is how I start my business talk. So this is not how I will start it here. So what is quantum machine learning? You take quantum mechanics, you take machine learning, and then something amazing happens. But let me try to get more into some more technical details of what quantum machine learning is, or what are the different types of work and research that we are doing that fall into the category of quantum machine learning. Okay. So one of the things that people have worked a lot on, including myself, is we want to start working on quantum algorithms for speeding up machine learning things. So we take something specific that people do in machine learning. Most of this has to do with linear algebra, because machine learning at the bottom is basically a lot of linear algebra. So can we use a quantum computer to speed up some of the computations that we do while we are doing classical machine learning, right? And there are two types, let's say, of categories of algorithms. I'm going to be missing many things. So if you see something that I flagrantly miss from the list, please let me know, right? It's not supposed to be exhaustive. It just needs to fit into one slide. So, okay, so one type of algorithms is things that have to do with linear algebra, right? I call them HHL type algorithms, right? This was what we did for recommendation systems a long time ago. Linear regression, support vector machines, PCA, there are all these results that use a quantum computer, and more particular, this type of singular value transformation algorithms to, in some sense, speed up linear algebra, okay? We can see how much we are speeding up or not, if these are, polynomial or what type of polynomial speed ups, but there is something that you can work on this type of algorithms. The second type of algorithms are algorithms where you can actually prove a speed up, right? Because that comes from things like Grover type quantum algorithms, like amplitude estimation to compute gradients faster, right? And these are mostly would give you this quadratic speed up on solving the problem than on a classical computer. And this you can actually prove it goes through Grover type arguments, okay? The HHL type, you can prove what is the running time of the quantum algorithms, but these algorithms depend a lot on the specifics of the data and on the instance of the problem. So they have all these parameters that in some cases they're better than the classical ones, but they have extra parameters in the running time that you have to be very careful to see whether in practice they give you a speed up or not. Things like the condition number of the matrices, the sparsity of the matrices, the rank of the matrices, and so forth. Okay. Okay, a second type of what we think is quantum machine learning is basically using quantum circuits as a quantum analog of neural networks. Okay? So again, here there are many different ways of trying to do quantum neural networks. The main idea is that in a neural network, you have some input, you take it through some layer, which is some linear transformation of your input, you get some output, right? Then you apply maybe some nonlinearity, then you give it to another layer, and so forth, okay? So here the idea is that instead of doing this classical, again, linear algebraic mapping from input to output, where you multiply your input with a matrix, right? And this is the matrix that you try to learn, right? The idea here is to have your input, pass it through a quantum circuit, and get some output at the end of the quantum circuit. So you're kind of, instead of doing this very precise linear algebraic matrix multiplication, you're trying to do something similar using a quantum circuit. Okay, and we'll see a little bit more details why maybe this will give you something more than what you expect to get from the classical case. Okay. Again, here it's very difficult to prove many things in the neural network case, right? It's very difficult to prove things like doing this quantumly will always give you a better result than doing it classically, because even in the classical case, it's very difficult to prove precisely which type of neural networks work or for what type of data sets they work and so forth. Okay, but there are many interesting questions here to even very theoretical questions that we can ask. Okay, so I'll also spend some time in trying to give you some ideas about trying to come up with, I mean, what, you know, one of the things I have been trying to ask myself for the last few years is, instead of looking at what classical machine learning people do and just try to speed it up, right? Is there something that for which quantum computers are natively good at doing that also has some applications in machine learning? Okay, so these could be things that maybe they're not so used in classical machine learning. Some of them are not, right? They have to do with, let's say, more difficult linear algebra or other type of computations. And the question is, can we use these more natively quantum algorithms to say something interesting in machine learning? Okay, so I think, you know, if you were at QIP last year, there were 3, 4, or 5 talks about topological data analysis. It's not, you know, we can talk more about it, and if this is the right use case. I will talk a little bit about these determinantal point processes, learning with subspaces instead of points, and this type of reinforcement learning with distributional algorithms that are quite interesting. And to me, they maybe at least there is an intuition why quantum should be doing good in these things. Okay. Okay. I'm going to finish with a couple more things. There's machine learning for quantum data, right? So this is another part of quantum machine learning. What happens if you have quantum data? Then obviously you need to do quantum machine learning because the data is quantum. I don't know of any quantum data. So I don't know where to find quantum data. So it would be interesting to understand if we will ever do machine learning with quantum data. And, you know, we can discuss it more, but quantum sensors don't give you quantum data in the sense of highly entangled multi-qubit states. They give you qubits one by one. So single qubits are not quantum data, right? You can write down 2 numbers, it's a classical data. Quantum data that come from quantum circuits also are not really quantum data. You have a classical description of the circuit. It's also classical data. So a lot of this quantum data, you can also very easily see them as classical data. But it's an interesting thing to understand where would this quantum data will come to us, and then we will have to deal with quantum data, right? Yeah. So, you know, imagine you have some process, some sensors, you know, that probe some system, and they spit out a 1,000-qubit entangled quantum state. So that would be a quantum data because you don't know how it got created by this physical system that you don't know what it looks like. It's possible. You know, what I said is that it's not possible. So, but, you know, yeah.
But maybe single qubits could still be quantum data if we don't know the qubits. I mean, we could write it into numbers, but maybe the source just gives us qubits.
Yeah.
So if we would want to get, so it's basically like a quantum sensing thing.
Yeah.
We could just measure them a lot of samples and then do classical machine
learning.
Yeah. But that's very wasteful.
I don't think it's very wasteful.
But I mean, in a
to
sense,
be honest.
quantum sensing is a machine learning for quantum data.
Yeah, all I'm saying is that this quantum data is very simple quantum data, right? They're single qubits, or now they started doing EPR pairs, let's say. So I think there will be we will get to be able to do classical machine learning by taking this data into classical data before we'll manage to do quantum machine learning on this type of quantum data, let's say, right? Okay, one other thing is, this goes into also this idea of, can we prove an advantage in quantum machine learning, right? Is there anything that we can prove we can do that it's not possible to do classically, right? And there has been some work recently, very interesting work that says, okay, let's look at the problem that has nothing to do with machine learning, but we know that a quantum computer is better than a classical computer. Let's say discrete log, okay? And let's design a machine learning problem where solving this machine learning problem basically would need to solve the discrete log problem, okay? So then you can say, okay, if I have a quantum computer, I can solve the discrete log problem, I can map, I can see it as a kernel, I can do this with a quantum computer, and we know that with a classical computer, it's not easy to solve discrete log, so this gives you kind of a provable separation between the two. Yeah, I think this is a very interesting theoretical exercise that it's to be seen if it has any impact in machine learning, actually. But it's still very interesting to see what's happening. Okay, and the last thing, so you see that I cannot write anymore, so this is the last line, quantum-inspired machine learning. Okay, so what do I mean by quantum-inspired machine learning? There are two different things here that you can think of. One is, again, all of the set of work that has come from looking at quantum linear algebra algorithms and saying, can I do this with randomized linear algebra, right? This is, maybe people call it dequantized quantum machine learning or dequantized linear algebra algorithms. So this is one part, right? So again, this is very interesting to understand what kind of separations we have and what kind of problems really we should think that the quantum computer can do something better, right? But you can see it also on the other side, which is that, okay, maybe quantum machine learning, or at least in the NISQ era, it could be about doing better classical algorithms that come from quantum ideas. And this is not the first time that this has happened. We have been working on quantum-inspired algorithms for many years. Now they happen in machine learning as well. If your goal is to actually solve the problem, I think this is a very interesting idea of, we have a different way of looking at things. Can we take this intuition and make it into quantum-inspired classical algorithms that actually work and actually solve the problem, okay? So, as I said, this dequantized one may not be the right thing if you really want to apply it in machine learning and use it in practice, but some of these algorithms over here, for example, this topological data analysis, instead of saying, okay, I'm not going to get a quantum advantage because of all these new classical algorithms, it's actually good, because people in practice do not use topological data analysis because it's very difficult to use. So if we manage to get better classical algorithms, that's also, I call it part of quantum machine learning. So it's good, okay? So now, the main question that, Umesh asked me to talk about is QML in the NISQ era. So let's do an exercise. Let's see which ones of these things we could imagine that they happen in the NISQ era. And I haven't defined NISQ era yet. I will define it afterwards so that we are vague enough to say what we want, let's say. So for any definition of NISQ era you can imagine, can we fit anything of this into the NISQ era? So I'll try to not be very controversial, but I'm going to put reds and greens on the different things. So red is thing that, let's say, we don't know yet that it's possible, but it may become possible. We should just work on it. Green are things that we hope they are going to be possible. So green is better than red, let's say. Okay, so are we going to see HHL-type algorithms or Grover-type algorithms happening in the NISQ era? It's very difficult. The reason is that it's very difficult to see quadratic gaps in the NISQ era, right? It's also very difficult to see HHL-type gaps where you need to do, let's say, singular value transformation, because the circuits are very deep. So these are amazing quantum algorithms, but are not simple ones that you can imagine running them with a few physical qubits or a few hundreds or thousands of physical qubits. So I would put it red, but I'm happy. Red means that we should work harder to make it green. That's the goal. I also think that machine learning with quantum data, we can do it in different ways. So also these quantum advantage ones, because we use problems where we have provable gaps, things like discrete log or factoring or things like that, it's not going to be simple to see them happening soon. This is obviously green because these are classical algorithms. I'm just saying let's get some intuition and do a classical algorithm. So this we can do. And then we have these two things in the middle where I want to be a little optimistic and make them lighter blue, lighter green. So it's not very green, but I wouldn't put them red yet. So the question is, can we get anything from this type of stuff to the green side, to the, to the NISQ era side? Okay. Any questions on this? As I said, this is just so that we have things to discuss in the next few weeks. Okay, so one more slide, and then I will go to actual results. Oh, I'm taking too much time. Okay, so yeah.
What is machine learning?
Oh.
Because it seems to be like any data processing on the slide before would be somewhere kind of.
I think, yeah, I mean, we can spend another full workshop on this. To me, it's things where you look at data to understand something so that you can predict something afterwards. So it's algorithms that need to learn in how to do things. But yeah.
Yeah, I don't want to cite it.
Yeah, I mean, let's discuss it afterwards. But to be honest, it doesn't matter. Let's say anything where, call it algorithms. Still, I would put very similar kind of things there, let's say, right? Yeah, any quantum algorithms in the NISQ era, even that, it's a very good question, okay? And I think afterwards we'll have the chemistry side, so this is what will complete, let's say, the picture. I'm not going to talk at all about chemistry, right? Okay, so what is NISQ era? Let me go a bit fast. I don't know exactly what it's NISQ, and it's not clear that John had a very precise, definition when he said the NISQ era. So, I would say something like 100 to 1,000 qubits with 100 to 1,000 depth, something like these gates. What I want to say a little bit is this thing, which is actually what we have an IBM person. So actually IBM is claiming that this will happen very soon. Okay? So if we believe what they say, and I'm very happy to believe what they say, it means that very soon we'll have 100 qubits that we can do 100 depth. Okay? That's a decent size machine. Okay? There is a caveat that if you want to get your result at the end, you need to do like many hours of post-processing, but that doesn't matter. I don't want to use it in practice, but if I can actually get results from 100 qubits and 100 depth, then that's a decent NISQ machine, right? So the question is, what can we do with this type of things, right? And then the other question is, can I trade off depth with qubits, right? So what is easier? I don't know what is easier to build somehow. I still think that this is easier to build, but do we have 100 qubits, 100 depth, or 1,000 qubits, 20 depth? Okay? And if you have this small depth, you better need to have all-to-all connectivity. 20 depth with nearest neighbor connectivity is not going to take you very far. But if you have all-to-all connectivity, like in ion traps and stuff, then logarithmic depth is very powerful, okay? So this is my definition of NISQ, is logarithmic depth all-to-all quantum circuits, or linear depth nearest neighbor quantum circuits with the same number of qubits, 100 to 1,000, let's say, okay? Again, I just came up with it last night, so it's not clear that this is the right definition of NISQ. But if we want to study a little bit more theoretically, what can we do in the NISQ era? One way of thinking about it is what can we do with logarithmic depth quantum circuits? Okay, and I'll give you all-to-all connectivity now, because you cannot touch all the qubits if you have logarithmic depth, let's say. Yeah. So what I say here is that if if I know how to get decent results with high probability for a computation that happened with 100 qubits and 100 depth, then I call this a NISQ machine. So there will be some noise, but I want to be able to get a decent result with 90% probability out of this calculation. So somehow I'm less interested on the qubits than on the computation. So the way I want to define it is that if I can do this computation, I don't care if the fidelity is good or what type of errors I have, or, you know, it could be that you have worse qubits, but the errors are nice so that the computation is possible, or that you have better qubits, but still you cannot do it, right? So I want to have an algorithmic type of definition of NISQ, which is I want to be able to do this type of computations. Yeah.
It seems like you're going between two definitions.
I'm going between 10, but yes.
But the two main ones have to do with constant numbers versus this other notion that's come up in, in the context of random circuit sampling and
Yeah.
other things where we say, look, we are just going to think about n qubits,
Yes.
volume depth, noisy.
Yes.
What can we do with that?
Yes.
And it seems like
Yes, so you see, I have one foot on academia and the other on the other side. So to me, I think theoretically, the first question we should ask is logarithmic depth circuits. But if you give me something which is 1,000,000 times log n, then this is never going to happen, right? Or but if you don't have logarithmic type circuits, then already you are screwed, let's say. But logarithmic depth circuits are a good starting point for me to say that something should be possible, right? And then we need to say what happens when n is 100 or 1,000, and log, if it is 2 times log, then you have depth 20. But it's not the same question, I agree. But given that I don't know how to ask theoretical questions with 100 or 123, I think logarithmic depth is a good place to start, let's say. But not asymptotic for n equals a billion, let's say. Okay? All right. So I think this is all I wanted to say, a bit general and stuff. So now I want to give you a couple of examples of what we have been doing on trying to get some of this quantum machine learning stuff into this NISQ era, and then in the end I will say how possible or not it is to actually get them into the NISQ era. Okay? So the first example I want to show you is this thing called determinantal point processes, right? So I'm getting back to this idea that there are some things that quantum algorithms or quantum computing is good at doing natively. And the question is, are these things interesting for machine learning or for algorithms in general? And whether we can actually, one more step, can we see something like this in the NISQ era? So the many stages, let's say, okay? So what are determinant point processes? Well, first of all, you have a bunch of points. A determinant point process tells you how to sample from these points, how to sample subsets of these points, okay? So here is a silly example. If you want to ask for a Jaguar, right? Your search engine can give you 3 cars of Jaguar, and that's great. They're very relevant results. But a different engine can give you 1 car Jaguar, the animal Jaguar, and the American football team Jaguar, okay? So these, not only are they relevant, but they're also diverse, okay? So you add this notion of diversity on top of your data, okay? So a priori, I want to say that this type of data is more interesting when you are doing machine learning, when you want to learn about data, than this type of data, okay? Now, mathematically, how do we define diversity and all of these things? It's very simple. You can think of every image as a point in space, right? And what you want to compute is the volume encapsulated by these points. So let's say I give you these 3 points. Because they're all 3 cars, they will be close to each other. They will be mapped very close to each other. So if you see at what volume is encapsulated by these 3 points, it should be small. If you get 1 car, 1 animal, and 1 football team, this should be far in space. So if you look at the volume encapsulated by these points, it should be large, okay? So the way to mathematically capture this notion of diversity is by looking at the volume between points, okay? And one more point to say that these determinant point processes, I showed you why they make sense with images, but actually they were defined in 75 to define the spatial configurations of fermions in optical beams. So these are exactly the distributions that tell you how the fermions will be in space when you leave them in some optical medium, okay? So it does have some quantum, native quantum origin, let's say, this idea of determinant point processes, and we will see that this also leads to a very efficient quantum algorithm, right? Because we are talking about fermions in some sense, okay? Okay, so a bit more mathematics. What do I mean by, by this notion of volume? So the definition of the distribution is very simple. You have an n by d matrix, and the question is, I want to pick a d subset of these rows n, right? And I want to pick each one of these d subsets with a distribution, with a probability which is proportional to the determinant of the submatrix, the square of the determinant of the submatrix, okay? And you think of the determinants as the volume of this thing. This is exactly what it is, okay? So the best classical algorithms to do that, after you do some pre-processing, imagine that this has been orthogonalized, so it's an orthogonal matrix, then you need a cubic time on the dimension d to actually be able to sample, to create a sample from this, okay? But imagine we need thousands or hundreds of thousands of samples when we train and so forth, right? So what we found is that we have a quantum algorithm. Think of d and n the same, let's say roughly the same order here. We found a quantum algorithm where you can do the same thing with depth d and d square gates, okay? It's not an enormous gap, right? So I'm certainly not going to claim that we will see in the NISQ era this particular gap, but I think it opens the way to something interesting to do, right? So I have one slide about how the algorithm works, right? And the slide is the following. I give you this matrix, these d columns of the matrix, which are orthogonal to each other, right? And what I tell you is that you need to be able to construct this state where S is just the subset of size d of these n rows that I had on the matrix. And the amplitude here should be the determinant, so then I sample S with probability exactly determinant square, okay? And this is the circuit that does it. I have the same type of circuit for each one of these d vectors. I do them one after the other, and at the end what I have here is exactly the state that I want, okay? So what is this circuit here? We call it a Clifford loader because it has to do with Clifford algebras. It's just a circuit that depends on this classical vector A1, that you put it in these parameters, let's say, and you can do them one by one and then get your outcome. Here I did something which has linear depth, so this is not good because then the depth would be d times n. But what we found is a logarithmic depth quantum algorithm to do exactly this part here. So if this has logarithmic depth and you have d of them, you have d log n depth in the quantum circuit, okay? So that's why I said that this logarithmic depth is an interesting thing to understand. It wasn't obvious that there should be a logarithmic way of loading these vectors here, okay? So this is a quantum way of loading this subspace, right? This d by d subspace, which means that you can sample from these determinants, okay? You can use it in machine learning because sampling elements is something that we do, for example, in random forests. I want to give you one example just to understand what I mean. Imagine you have two types of data. You have the purple data and the yellow data, okay? And you have a lot of the data in the middle, and then you have some purple on the left and some yellow on the right, okay? And now you want to understand how should I split, what kind of decisions can I make so that I can figure out if a data point is purple or yellow, okay? So it's pretty simple to see what you should be doing. You should just say, okay, if my feature 0 is less than -2, then I'm going to predict purple. If my feature 0 is more than 2, then I should predict yellow. And if it is in the middle, then just guess. Everything is there, okay? So this is what we do in these decision trees that we use in the random forest, right? And the idea is that how easy it is to actually find these things, because here I gave you a two-dimensional example that you can see it. If I have elements in 150 dimensions, it's not so easy to figure out what are the right, splits. But in this simple example, we did a test and we said, okay, imagine that you're just uniformly picking elements, which is what everyone does in machine learning to do random forests, versus if we use these determinant point processes to pick subsets of the data. Okay? Do we gain anything in this very simple example? And here is what we gain. The probability that my DPP sampling will actually find these two correct splits is up here. But if I uniformly pick, what will happen is that I will only pick things from the middle. And then it's not clear that I will do the right decision, right? So the probability that the uniform sampling will give you the right splits is much, much smaller. Okay? Again, this is a very simple example to see why DPPs are something that in practice actually work. Okay? We also tried it in many different data sets and it actually works in practice. And I have a slide about can we actually prove mathematically that using DPPs for random forest is actually a very good thing to do. So what we can prove is that DPP is the optimal distribution to reduce the variance for some particular cases, like the linear regression, the support vector machines, because these are more mathematical, decisions. We cannot prove the same for a random forest, because a random forest kind of arbitrarily makes decisions to split, on some feature, should I go left or should I go right? So there's not enough structure, let's say, to do it. But if you look at some sort of heuristic properties of the random forest and you simplify a bit the model the same way that we did it in the previous example, what you find is that it reduces to something that we know that the DPP is the best case. So at least in some simplified case, the random forest, you can prove that the DPP is the optimal distribution to pick in order to maximize your goodness, let's say your performance. Okay? There is a lot to be done here. I think there is some very interesting mathematical questions of are these distributions, can we prove something more about these distributions when it comes to all these machine learning models, these random forest, XGBoost, and so forth, anything that uses these decision trees. Okay? Okay, maybe last thing, because I do want to speak, I have 5 minutes, Wow. Okay, so I want to speak, okay, are we gonna see them in the NISQ era? I think it's very difficult to see it if we are sticking with the particular task where classically you can do it in D cube and quantumly you can do it like this, okay? But this is not the end of the story. The quantum circuits can do many more things than sampling from the DPP. We kind of thought about the DPP because this is what classical people are doing, okay? But these quantum circuits can do many more interesting things, which is, for example, sampling from mixtures of DPP distributions, or things that classically we shouldn't be able to do them, okay? The quantum algorithms remain the same, like we can still do them very efficiently. The question is, are any of these things actually useful, right? It's not very clear, right? But I think it's worth understanding what more can we do from the DPPs. For example, DPPs are fermions. If you go to bosons, you have permanent sampling. This is also something very interesting. Here you don't pick diverse things, you pick close by. So you have determinants, you have permanents. You can even go into a superposition of fermions and permanents. Are any of these things useful and interesting for machine learning? It's not clear because no one has ever used them, right? But I think it's worth, trying to understand if anything can come here from these discussions. Okay, I have 3 minutes, so I wanted to talk about neural networks. So, yeah, 5 minutes? Okay, thanks. 7, okay, good. Good, because either I will butcher it if I do it in 3 minutes or, okay. All right, this is my last topic, the neural network. So I want to try and understand why should we care about quantum neural networks? What are the things that we can add to classical neural networks? Is there anything that classical neural networks cannot solve? So let me try to define what is a quantum neural network. First of all, we need to load some data, right? As we said, we load some data to a quantum circuit, we do some operation, and then we see what happens afterwards, okay? And this operation is the one we try to train, so that what comes afterwards will tell us if it is a cat or a dog, okay? So loading data is already very interesting question. There are many different ways of doing it. We are mostly using this thing that we call a unary amplitude encoding, and I'll tell you why, let's say. But what we do is that if you have an n-dimensional vector, okay, we use n qubits, and we put in the amplitude the coordinates of the vector, and then you have a unary state. A unary state is all zeros with 1, 1. Okay, so you have n states. So in some sense, this is very wasteful because I'm using n qubits for an n-dimensional vector instead of a 2 to the n-dimensional vector. Okay, what I gain by this is that I can also load it in log depth instead of having an exponential depth of trying to load this thing. Okay, so this is one way of doing it. There are other general encodings that you can say, I just take each one of the coordinates and I rotate my qubit. Okay, this is a different way. This is another interesting way, which is that you do this and then you do a Fourier transform. You do a Hadamard. So now this is all possible 0, 1 states, but it has encoded also in the amplitude the vector. All right. Once we have a way of loading the data, then we need to have some parameterized circuit that we will call a neural network, meaning that they should have some parameters, and then we need to find the right parameters, and this will give us the trained neural network. So here what we use again, we go back to fermions. So these are kind of fermionic gates. These gates here, they're all the same with different parameters, and these are the gates. So it's just a rotation on the 0, 1, 1, 0 subspace, and an identity on the 0, 0, and 1, 1. Okay? And we put them in some different configurations. Okay? What are the properties of these things? They preserve the Hamming weight, meaning that there are no ones that are created or destroyed, right? If you put as an input here something that has 3 ones, you will end up with something here that has 3 ones. Okay? None of these gates here changes the number of 0 and 1s. It just rotates between the 0, 1 and 1, 0. Okay? This, which means that basically if you look at the unitary, it is block diagonal on the subspaces, which are the Hamming weight subspaces. So this is the Hamming weight 0, the Hamming weight 1, 2, and so forth. Okay? So the way that this thing works is basically a different unitary for each one of these Hamming weight subspaces. Okay? What is very interesting is that if you look at this pyramid architecture, this you can prove that this gives you exactly the orthogonal group on n by n matrices. Which means that if you look at this matrix here, which is the matrix that corresponds to the unary basis, right? This is an n by n matrix, and by tweaking these parameters here, you get all possible orthogonal matrices. Okay? Which means that if I start with an input which is unary, and I apply this, then I'm doing basically something classical, which is I apply an orthogonal weight matrix to my input. Okay? So at least I can do what a classical neural network does, which is apply a weight matrix on my input, with the extra property of orthogonality, which is a very interesting property to have in machine learning because it keeps your features uncorrelated, and this gives you the maximum information that you can. So orthogonality is a good thing. Classically, you don't know how to get orthogonality. apart from orthogonalizing the matrices, which you don't want to do because it's a cubic operation. But quantumly, you get it for free somehow, okay? So as I said, if you put a unary data loader here, basically what this matrix does, instead of doing a 2 to the n by 2 to the n unitary, you can think of it as doing just an n by n unitary that goes back to what the classical thing would do, right? The interesting thing here, and goes to these quantum-inspired things, is that it was not known how to do a gradient computation and how to update these orthogonal matrices by keeping the matrix orthogonal. So what people in classical machine learning were doing, if they wanted to keep this orthogonality, was to look at the matrix, compute the gradients of each one of the elements. This gives you a matrix which is not orthogonal, and then do an SVD to orthogonalize the matrix. This is not something you want to do while you train, and this is why no one was using these orthogonal neural networks. If you look at the neural network, as we said, as this is a way of parametrizing the orthogonal group that now you can compute the gradients in constant time for each one of them, which means that you can do the entire training of these orthogonal matrices, even classically, in n squared time. So now we know how to get this extra property without spending any more time than if we didn't have the property, okay? There's not much quantum here because I'm saying we're just working in an n by n space. This is classical. But if we don't use the unary loader and we use a different data loader that goes to all possible Hamming weights, right? Then you do have an exponential size matrix that is applied, okay? What is usually the problem with these exponential size unitaries is that it's not clear whether they will train, because now you're in an exponential size space. This is fantastic because maybe you can find better optima, but you're going to get lost very soon, like your gradients will be very close to zero, okay? But what we can prove for these things is exactly that they are trainable, okay? And the reason is that there is a very linear algebraic way to define what these matrices are. If you know what this matrix is that you get from the parameters here, then these matrices here are just the compound matrices of your original matrix. So there is a very precise, algebraic definition of what these matrices look like. And if you look at what they do, are basically having DPP distributions on each row of the matrices. So all of this is very much related, again, to fermions, to the distributions of the fermions, and how you can use all of this to train neural networks. So I finish here. And I'm going to you can do transformers, you have many applications. I'm just going to go to my conclusion slide. I was very optimistic. Everything works, everything is great. Okay, so this is what we said so far. I tried to convince you a little bit that there is hope in working on this thing to be able to get some application in the NISQ era, right? And my concluding remarks is that quantum computing has the potential to improve machine learning. Quantum algorithms can provide provable advantages in the future. If anything works at NISQ, then it will probably be QML. It's much easier to make QML work than chemistry, because chemistry is a very precise thing. QML is not very precise. And if we find something interesting, then it is not going to be TCS provable, but it's going to be machine learning provable, and we can talk about what this means. Quantum neural networks could provide advantages. It has to be seen. It has to be experimented and see if it works in practice. And on our way to try to understand what kind of NISQ quantum algorithms we can get, I think we can turn some of these quantum ideas into very powerful classical solutions and offer a lot to classical machine learning even today. Okay, all right, thanks, and sorry for taking over time.
All right, our next speaker is Abhinav Kandala from IBM, and he's going to tell us what we can do with a noisy quantum computer.